If I have a conductor and I put plus Q here, this we discussed yesterday, you can think of the situation as though that you have actually minus Q, exactly diametrically opposite to the plus Q inside the conductor. Okay? And of course, this is just an image. This is not a real charge, right? This is an image. This is a mirror image of plus Q, and it has a minus charge. Right? And the field line goes like that. Okay.
What keeps it? I mean, when you erase it and then assume like the fixed like, I mean, what keeps it from going radially outward up? Is it just the conductor? That makes the positive.
Yes, yes. Well, you also have a field line. Eventually, it has to close. I mean, electric field line either has to add at infinity or add another charge.
So it can't just keep going upwards?
I guess there's one line that you can keep on going upward.
Oh.
Everything else is slightly deviating, and actually it always closes in on the minus Q.
But if there is no minus Q.
Right, there's no minus Q. That will end on a conductor. This goes to the pin. Okay. It always ends on a conductor. So the solution above this is C equal to 0, this is C greater than 0. The solution above the C equal to 0 plane, right, is the same solution as though you're having plus Q and minus Q here. Right? But the solution at C less than 0, the solution here is all identically 0. Right? And this is the top half solves the same Laplace equation.
And it has to go down in a perpendicular.
Yes, it has to be perpendicular. Yes.
So if there wasn't a conductor there, it would just radiate outwards from the plus Q, right?
Correct. Yes. Suddenly, I put the conductor here. It changes the boundary relation for the Laplace equation. Right? So everything actually had to become 90 degrees here. And if you solve for plus Q minus Q, right, at the bisector, the electric field between plus Q and minus Q at the bisector, right, you'll find that all the electric field is going like that. Right? And also, we did see that yesterday lecture, the potential at the bisector is equal to 0. Right? So that's the reason I can claim that the top half of the solution is exactly the solution of plus Q minus Q quote-unquote dipole. Okay. So, I mean, this is one problem. Another one problem, this is actually very useful. You can do many things with this kind of method. Suppose I have a sphere, a conducting sphere. Right, of radius r. Right, and if I put a plus Q here, okay, what is the distribution of charges on the conductor? We know that it will be polarized like that, right? It's all minuses here, right? And if this is neutral, if I care about this side of the solution, then this will be positive. Right? Okay, and we can solve this. It's done in, you should really read through the book. It's in problem 313. I think 313. Yes, 313. There's a solution. And you just have to go through the solution in the back. And what happened is there is an image charge here, minus Q, and the relationship between the magnitude and the distances are as such. If this is given by A and this is given by small a, right? Then small a is just r squared over a. I'm just copying. I haven't done this probably in a long time. R squared minus a, and then the charge minus q here is equal to r over a. This solved the situation where you have a plus q above a sphere. And the whole thing is symmetrical. And it's actually property of problem 313, right? If I have a conducting sphere, this is the real charge, by the way. This is real. This is image. Right? But if I have a situation where this minus q is real, right? Then the image is exactly that plus q here. This is real, this is the image. Then I have the same relationship. This is the center of the sphere. This is R. This is A. This is A. Right? This still holds. Right? Except in this case, it's this thing that's real. Right? It's the charge inside that's real. The charge outside is the image. Right? It will still solve the same Laplace equation outside.
And will the field line still look the same?
So what happened? The field line looks, yes. Depending on whether you get plus or minus, right? The field line is still the same. And everywhere it has to be normal. Right?
So like when it's inside the conducting sphere, like it's supposed to be 0, right? Or like it's past
No, no, it's supposed this is a conducting shell.
Like the V is supposed to be 0.
Sorry?
The V is supposed to be 0?
V is 0 here. On the surface here, on surface, V is equal to 0.
So the field lines will be coming from outside to the?
Yes. Oh, in this case here, sorry. No. I need to actually do more carefully. Here, in this case, the image is on this side, right? So you have a field line that goes like that.
From inside?
From inside, yes. Yeah.
Can you get outside or does it affect outside?
Well, in this case, outside is not as well defined. It depends on what you're trying to do here, right? The potential here is 0. Right? So it's the same as the potential at infinity. So if I'm interested in solving for the solution of the Laplace equation inside this sphere, right? Then I'm considering everything else is 0. So consider this to be just a conductor like that. Yes,
Why do you have the small a is equal to r squared and big A?
Oh, this you have to solve for it. I don't want to solve for it today here. There's a lot of algebra. But if you solve for the potential created by these two charges, right? Solve for V at any x and y in such a way that this is the potential is given by the potential that comes from plus q plus the potential that comes from minus q, right? And set it equal to 0, right? And you'll see a solution for a circle, right? But I'm just doing it in x, y. The whole thing has cylindrical symmetry, right? So if the solution is a circle, you can rotate it around the x-axis, you get a sphere. Yeah, just take my word for it or go through the solution in the back for problem 313, exercise 313. Okay. It will give you the image charge for a sphere. So with that in mind, there are two interesting problems here in the homework. First one, let's do the first one first. So what you have is something like this. This is number, I don't know what number this is. Has anybody looked at the homework yet?
This is 47.
47 is, So what you have is a plane conductor, right? And then you have this form here, a hemisphere of radius r. Okay? And you put this q at 2R. Okay? Okay? And you're supposed to solve for the charge distribution over here. Right? Or all you need to do is find the image charge. Because once you find the image charge, you know where the the charge distribution is. Right? So how do we do this problem?
And it's similar to, there would be an image chart in the inside, right?
So we have a conductor here, it goes all the way to infinity. So the potential here is 0, right? Anywhere on a conductor, P is equal to 0. This is all inside the conductor. But this is kind of a hybrid between a plain conductor and a sphere, right? So how do you do that?
Wait, is it saying that inside is a solid conductor, or is it
Yeah,
just
solid
a
conductor.
single? Okay.
Solid conductor. This is a solid conductor with a bond.
Could you do this with intense?
Yes. You do a principle of superposition. That's right. So this is kind of. Again, what matters is the solution above, right? I don't care about the solution below. The solution below is 0. All I want to make sure is I can match the solution in this space. If the solution in this space satisfies the same Laplace equation, then it has to be unique, right? That's the whole idea. So if I write that configuration as a superposition between a flat conductor plus a sphere, okay, and set the potential of this equal to 0, and the potential of the sphere is equal to 0, right? Then this had to become that, right? Because the potential is 0 everywhere. It's 0 everywhere here, it's 0 everywhere here. Okay? So I just have to find a solution that I can superpose, right? By having a plus q here. This is 2r. Right? And another plus q. This is also 2r. Okay. So where are the image charges? This one, the image charges is exactly 2r minus q. Okay? How about this one here? This one here, you have an image charge over here, right? Just follow that equation over there, right? So you have minus q here, and then use those relations to find the distances, okay? And let's not bother to do that because we can do that at home, right? Okay, so you have minus q here and minus q, right? But that's not enough, is it? Is it enough? No? Because what happened is that this minus q, this image minus q, right, is above the surface. Right, so you must have minus q here. Right? So that minus q will have an image plus q over here. Right? So if you look at it, let's see, the plus q will have a solution like this, right? Yeah. And the minus q, well, there is a relationship between plus q and minus q, but that's on this side of the solution, right? But between the minus q, the small q, we have something that looks perfect, that will like similar. The field line is going the opposite direction. Right? That ensures that the field line is coming from this minus q. This small minus q is actually normal on this plane. Right? Otherwise it won't, right? If you just have that. Am I explaining this very well? Maybe I don't understand it pretty well now. I think this is the solution. Any idea? Is this confusing? It's confusing, but I'm a bit confused too. Let me think about it more carefully. But the idea is that
Well, I thought B was equal to 0 everywhere, even on that like home plane. Why is the line?
it's a zero everywhere here.
Does the line just dominate because like that?
Which line?
The long line, the infinite line. As if it was two things, as if it was a sphere. Because you said that the minus q also has an image across that line.
Right, yes.
Everything has to be reflected across that line.
No, not necessarily. This is the part that I just cannot think on the field right now. But what happened is everything below here is unreal. Right? This is an image. Right? But putting minus q over here, right? This minus q here, the image of plus q on the hemisphere is actually above this line. Right? I'm interested in solution above that line. So this minus q will have an image over here. That's so at the end of the day, this is what you have, right? What you have, the solution is plus q minus q here as an image, another image here, another image plus q here, right? And another, this is the image of that on the image of this charge here from that plane, and then I have minus q here. This is the final solution. And the subtlety is just this two, right? Where does this come from? Right? But this is the image of that minus q because of that plane.
So it's essentially the image of the top cube. I mean, right?
No, I have to compensate. Basically, I have to compensate. That's the Let me think about it more carefully, and I'll give you a much more definite answer tomorrow.
But how far is this second plus q from?
This plus q?
Yeah.
Oh, it's equal distance. This is A, right? This is also A. Right? Because this plus small q here is an image of this minus q from that plane.
Yeah.
Right? If you're confused, don't worry, I'm slightly confused too. I'm only 95% certain of my solution. But tomorrow I'll be 100% certain. I just cannot think of enough. Sorry?
No,
Yeah, don't think about optics still, right? Think about records. Think about image charges. Yes.
So the only thing I don't get is on the right image you're trying to replicate electric potential around that sphere.
Yes.
Then why would you go to plus q? Don't you have it solved with minus q already?
No, I have plus q here on top of the sphere. That gives me an image of minus q.
Right.
Minus small q, right? Given by that relation.
Okay.
He's asking me why isn't there a plus q up in that diagram as well? If you added one here, then why isn't there one up there? Is it because this is superimposed on the slab of conductor?
Yes.
Is that why there's an image that's...
If you were to look at that slab,
No, the whole thing is not exactly symmetrical.
Okay.
Right, we're looking at solution on this plane here, right? So I see your point, right? Why isn't there on that, right?
Yeah.
That's the part that makes me uncertain about the solution. Why isn't there a image of this minus q on that sphere? Right.
Yeah, why don't we minus large Q on this guy.
Yes, 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 that's the part that I'm confused about. I'll get back to you tomorrow. Think about it, we can discuss more about this tomorrow. I don't want to just take all our time. Right? But I'm pretty certain that the solution is that. Right? The only uncertainty is why isn't there an image of minus Q on that sphere? And the reason there isn't is because I'm not. This is imaginary. This is not real. This is an image. The real thing is happening over here on above this plane. But I might be wrong. I mean, question.
It does have that minus Q from the slab, doesn't it?
From the slab, this plus Q. The only thing that's real is this plus Q.
Yeah, but then the minus Q is reflected over
Here,
here.
right?
And then you also have this plus Q, that is, so you can like reverse the whole thing, so look at it upside down, and then you have this minus Q's image is
Plus
that one,
Q, right?
and then that plus Q is the images inside the
No, it's not, because here, the boundary condition is very different.
If you had a
No, the boundary condition is different. Here, you can have a gradient of potential here. You cannot have gradient of potential here, right? The potential everywhere here is zero. That's why the whole thing is not symmetrical, right? This is not a symmetrical problem. This is not like a mirror where it's completely symmetrical, right? Here, the potential is all zero. Right? That's why there is no image of this minus Q on that sphere. That's the reason there is no image of that.
Wait, one more.
The potential inside the meat of the conductor is zero. Right? So there's a potential gradient over here. Right? So the situation is not completely symmetrical. Right? We are only interested in the solution above this plane, above this conductor. Right? So there is no such thing as the image of this minus Q on that.
But that's just a sphere, and when they're together,
I don't know. Yeah, let me get back to you on that. Let's move on. Let's move on. Sorry, I didn't nail it down completely. It's tricky, right? There's another. The next one is also a very tricky problem. I have an infinite slab. This conductor. This also conductor. And they connected, and the potential is zero. It's zero. Right? This is problem. See, do you know what the problem is? This is problem. 37. Right? Number 37. Okay? And this is the y direction. We call it the y direction. This is y equal to 0. This distance is s. And this distance is v. And I put a plus q here. Okay? And then you're supposed to find the charge distribution on the conductor. Okay? Let me just remove that just to make sure that's kind of asymmetrical. So how do you solve this problem? So that you might have an infinite iteration here. Because if you have a plus q here, it creates an image minus q. On that one, it creates another image of minus q on this plane, right? Okay. But then you have an image of this minus q along this conductor somewhere over here, right? Become plus q, right? And then the image of this minus q from this plane somewhere over here, right? And this goes back, on and on and on. Okay. Of course, all the images get farther and farther away, and they become less and less important. Right?
Where is B zero on these?
Say it again.
Where is B equal 0 on these? Is it inside of 0 or on the slab?
a V0 on the conductor. So the conductor goes all the way to infinity, and they connect it. The potential is 0.
Wait, why is there a negative Q on the far right?
Is this a slab?
This is a slab. Yeah, this is a slab in C. Just like an infinite plane.
Going
It's
up and-
going up and down.
Okay.
Exactly. Like a wall, right? There's a wall here and there's a wall here.
Yeah, we're just getting there.
So,
Wait, why is there a minus Q on the far right?
oh,
Is that as far
first
as-
this is the only real charge, right? Right? There is an image of this plus Q on this minus Q. This minus Q is an image of plus Q.
And how far is it from, is it exactly the same
Wait, why is
distance?
that?
Yes, this distance here is S minus B. This is also S minus B.
Oh, that makes sense.
Okay, did I draw this too far?
Yeah.
Okay. So think about it. If this B is really small, if plus Q is somewhere over here, right? Then you have minus Q over there. Right? Then this is all that matters, right? If this is so close, right? Then all the field lines just get concentrated in this dipole. Right? And the image of this plus Q from this plane is somewhere over there. Right? Minus Q is too far away. Right? So the charge distribution here is very small.
Wait, can you go over that one more time?
Right? I'm saying that the iteration, you have to stop at this one iteration. If plus Q is so close to the left plane, right, then you have an image minus Q next to it, right? And basically all the field lines will be concentrated in between this dipole, right? Leaving almost nothing on the other side. Right? I mean, think about it. If this is so close, plus Q and minus Q, they pretty much cancel one another, right?
I understand that, I just don't understand why they would be so close to.
No, if you put them, I'm just trying to understand the problem. If I put them so close together, right, then there's no image charge over here, right? This is almost neutral. Okay. Right? If they, how about if they're exactly in the middle? If they're exactly in the middle, then this is probably just Q over minus Q over 2 here and minus Q over 2 here, right? Half the field line go that way, the other half goes this way, right? Okay.
And Y over 2?
Because the field line has to start at plus Q, it has to end.
Oh, right on, yeah.
If you're exactly in the middle.
Because then we have an image.
And if you're very close to the left, the image is just here and there's nothing here. Right? But how about if you're in some arbitrary position from the left plane, P? Right? That's the issue. Right? This is where it's difficult to solve, right? Because if you think about it, right, the field line goes like this, but some goes that way. Right? I want to know the ratio between Q1 and Q2.
Is that what we're looking for in the question?
Yes, that's the question.
It's just the ratio.
That's it. So how do we do this?
Oh, it's a magnitude of it.
So the way to do this is actually not solve these image charges, right? Because to solve it with image charges, it takes forever, right? Because you have to iterate.
You get an answer if you.
Ramsey, you have an idea? You smile. You have an idea to solve this?
Yeah, I was smiling.
No. Oh, I thought you already solved it. No. You just smiled. I thought you have a solution. So again, yes.
But if you keep going, would you get an answer?
Yeah, you get an answer. Yeah, because all the subsequent order in the iteration gets smaller and smaller because the image gets farther and farther away, right? And they matter less, right? But yeah, maybe it will converge. Right? There will be a solution, and you can try to do it that way.
No, I don't think.
Maybe it's actually doable. If you sit down, I'm sure you can do it. But to solve this problem easily, is you want to exploit a method of superposition. So I put plus Q here, right? I can put plus Q here again. The solution will add, right?
Yeah.
Right, whatever image charge is created by that will be the same image charge is created by another plus Q slightly underneath it, the whole thing slightly displaced, right? So I can keep on doing that, and I can build myself another wall, right? Okay, so let's imagine that instead of having plus Q here, right, I have this plus Q spread uniformly across this wall, along this wall, right? Just a thin sheet of charge, right? With the sigma given by Q over A, right? The A eventually cancel. The A is just the area of this slab. Okay. 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 So now the question is, of course, this is your conductor, right? Everything of this thing going to infinity, right? The potential is 0 here, potential is 0 here, right? So now you want to solve for the sigma 1 and sigma 2, right? The reason that we do it this way is that we don't have to worry about variation along the plane, right? The solution will be homogeneous along the plane, right? Yes.
But you still have to worry about variation and
Yes, this is still P.
this is still okay.
Right, and this is S. Right? I just want to make sure that the electric field is all the same everywhere, right? In this case, you have electric field like this. And I have electric field like that. Right? From that. Okay.
And it's the same thing as infinite, and why are they?
This is an infinite slab, just like what we used to have. A lot of our example talks about the field coming from an infinite sheet of charges, right? So this is what I have, an infinite sheet of charges, except it doesn't end at infinity, right? A distance s minus b away, there is another wall with potential 0, and the distance b to the left, there is another wall, potential equal to 0. Right? Okay. But this is a much simpler problem because all the electric field is constant, right? Everything is constant. If you have that, it's too complicated.
But what's the reasoning behind why we can make that system of the elements of
By principle of superposition.
Okay, what are we superposition?
Oh, if I have plus q here, right? I can put another plus q here. Right? It has its own solution, right? But it will have the same solution because I have the whole thing. I can translate the whole situation in along x plane. It will give you the same solution translated.
Yeah. Oh, okay, that's fine.
So I'm building that. I'm building this sheet from all these differential
all
plus
ones. Okay.
a lot of plus cubes, right? All the way along this wall, right?
Well, why can you do that? Like, it doesn't change anything
No,
by
because
adding.
the ratios are going to be the same.
The ratio will be the same. By principle of superposition, the ratio will be the same. Okay? So then, this is applying everything you know about electrostatics so far, right? We have an electric field here, let's call it E1, E2, right? And then this is sigma 1, this is sigma 2, and this is sigma, right? Okay? So, what do we do here? What's the potential difference between these two places? Delta V1.
On the outside,
E is 0 here, right? And E is 0 here.
E0
Right.
minus U1.
The electric field is constant,
We didn't know the distance.
right? And the distance is B. This is S minus B,
Plus BEI.
right? This voltage, this potential difference here is E1 times B, right? Just the line integral of the potential difference is just E F, right? And that just gives you that. The potential difference across the second plate is E2 S minus P, right? Because this is S minus P. Okay? And they have to be the same, right? Because this is, I'm taking the line integral that way. Let's just denote the line integral with the wiggly line, right? This is another line integral. The potential is 0 here, the potential is 0 here, right? So delta V, it ends up on the same plate, right? Delta V1 is basically the potential difference between this wall with respect to 0, right? Delta V2 is the potential of this wall again with respect to 0. They have to be to the same potential, right? So this is equal. Right? So I have E1 equal E2 has to be equal to, is it S minus B? No. No. Right? S minus B over B, right? Okay? And then you already solved the problem. No?
What was it actually asking?
Asking for the,
Oh, the charge.
the ratio between Q1 and Q2. Because what happened here, right? Remember, again, for a conductor, always remember this, right? There is a reason why I emphasize myself a lot. Across the surface, right? So if I look at the these three sheet here, this is sigma 1 here, and this is sigma 2, and there's an electric field here, E1, right? E2, right? Then sigma 1, and the electric field is 0 here, electric field is 0 here, right? Okay? So that means what, just applying this equation here, then E1 is equal to sigma 1 over epsilon naught. Right? E2 is sigma 2 over epsilon naught. Right? Just the magnitude. Right? The fact that the arrow is pointing towards the wall means that this is negative and this is negative. Right? Therefore, you can find the ratio of sigma 1 to sigma 2. And this ratio is exactly the ratio of Q1 over Q2. Right, by principle of superposition.
How does that supposed to be?
And it's crystal clear, right? Yeah, pretty. Yeah.
How that's supposed to be E2 minus E1?
Yeah, E2 minus yes. Basically, along any surface, this is also another one of the statements for electrostatic. Right? Any surface with the surface charge density, the normal part of the electric field has a discontinuity equal to sigma over epsilon naught. It's always true. And of course, the other part of this equation is that E2 minus E1, but now it's along the parallel direction is there. Right, along that this is the surface. This is normal, this is parallel. So the electric field is always continuous across the surface. Right? But the normal part of the electric field is not.
And this is true for one cube, like one
No, I'm just building this by principle of superposition.
No,
That if I solve it for the wall, if I solve it for the wall and I know the ratio, right? And the same ratio has to be preserved by the principle of superposition for this,
Yeah,
right?
okay,
Meaning
yeah.
that
sigma Q.
Basically, I'm doing the inverse of the principle of superposition, right? From just 1 plus Q, I build a wall, and I exploit the principle of superposition. Once I find the answer, I work myself backward, right? To show that sigma, if I know sigma 1 over sigma 2, then it has to be the same as Q1 over Q2.
Oh,
Okay.
So are you saying that statement over there is equivalent to this statement?
And
E1 over E2 is equal to S minus B?
No, meaning that E1 over sigma 1 is equal to epsilon naught E1, sigma 2 is equal to epsilon naught E2, right? Therefore, sigma 1 over sigma 2 is equal to S minus B over B. Correct. And basically solving this is completely.
yeah, it is.
Okay.
How many people come to a class? This is like 20. And we always, as usual, we always missing Peter. So this is equal to Q1 over Q2.
Okay, so it is equivalent then. Yeah. So we're working backwards to the solution.
Yeah. Many years ago, I was TAing for physics 112 when I was in grad school. Like early in my grad school time. And I was TAing for Eugene Collins. I don't know if you guys know Eugene Collins. He's one of the famous professor at the physics department. He's the only Berkeley professor that won the teaching award twice. Right? And I had to be a TA for his 112, and he told